This is the first lecture in a series of lectures covering the time domain response of first order systems. And we're going to begin, in this series we'll be looking at both circuits involving capacitors and inductors, and we'll be going back and forth between the two of them. And what we want to begin with initially is to look at a capacitive circuit. So here's a list of some topics that we'll be talking about. We'll be looking at KCL and KVL equations and first order differential equations that result from basically formulating the KCL or KVL equations when a capacitor or inductor is in the circuit. We'll look at the state equation, what we call the state equation. We'll look at a discrete time approximation solution. And we'll look at the state equation versus node or slash mesh equations to do a comparison, trying to relate what we're now discovering with capacitor and inductor circuits, relating that back to what we learned when we were analyzing pure resistive circuits. We'll then look at solving first order systems. Okay, and we'll look at what is called the homogeneous or natural response of the system. Secondly, we'll look at the forced or particular, sometimes called particular solution or response. And then we'll combine those and look at the complete response. Okay, so the natural response, the forced response, the complete response. We'll look at network reductions, and first order systems, first order circuits. And then we will look at piecewise constant sources using the unit step function. So eventually we want to arrive at being able to consider voltage sources or current sources that drive or power our circuit, which are no longer just constant like a DC battery, but maybe they switch between being 5 volts and then 10 volts and then 5 volts and then 10 volts. And if they should step once or step up and then back down, can we find the time domain solution of how the circuit responds to that? Okay, so it's not just any arbitrary type source. We have some pretty tight constraints here, but we'll look at something a little bit more interesting than just a pure DC source driving our circuit. Okay, and then perhaps at the end we'll have a lecture on an RC oscillator. Okay, which would connect with some, relate to some lab activity down the road. So it'll take several lectures to cover all of this, but we'll get started. So KCL and KVL equations of first order circuits. Okay, so let's consider a simple three-element circuit involving the voltage source, a resistor, and a capacitor. Okay. This will be Vs. We'll call the voltage across the capacitor Vc. We'll call the current I going around the loop. It's also IC. And we're going to write a KCL equation. Okay. We'll write a KCL equation, and we'll write that at this node right here between the resistor and the capacitor. And maybe we'll do a KVL equation afterwards. So let's do a KCL. So we're going to sum the currents leaving. So we have IC, okay, we'll call this IC, the current flowing through the capacitor leaves, plus we have VC minus VS over R is leaving, and that's equal to 0. Now, recall that for a capacitor, the constituent equation that relates voltage and current is IC, the current through the capacitor, is equal to the capacitance times the time rate of change of the voltage. Right? We can put that in an integral form, where we can say VC of t, VC is equal to 1 over capacitance integral of IC dt. Okay, and we could get our, it's IC of tau d tau evaluated from minus infinity to t, or we can write it as 1 over c integral from 0 to t of IC of tau d tau plus some initial voltage on the capacitor. Okay, so that's the integral form. Right now we're going to use the derivative form, differential form. We're going to replace IC with C dVc dt. Okay, and this is a choice I'm making. I'm deciding to write one equation in terms of the capacitor voltage. Now, if we were writing node analysis, which we are doing node analysis, we want to write an equation in terms of the unknown voltages. We really only have one unknown node voltage here, right? Because the other node has a known voltage of Vs. So by doing this replacement of IC with C dVc dt, I am in fact writing a nodal equation that involves our one unknown node voltage. So let me clean this up and put all the terms that involve the capacitor voltage on the left side of the equation, and I'll put all the other terms, which is just VC, Vs, on the right side. Okay, and we have this equation here. RC, R times C, the resistance times the capacitance times the time derivative of the capacitor voltage plus the capacitor voltage is equal to the forcing voltage. Okay, and we can put this in a slightly more standard form. We can write this as tau dVc dt plus Vc is equal to Vs, where for our circuit tau is equal to Rc. Now the reason that tau is chosen is if you look at the units of R times C, or of tau, it must be time, because we are adding the voltage Vc to tau times the derivative with respect to time of Vc. So the derivative with respect to time will be volts per second, and that's times tau, and that has to be equal to volts, so we can add it to Vc, which is volts. Okay, so tau is units of seconds. Now we could write a KVL equation as well. Okay, so maybe you see a single loop, say, oh, let's write the KVL equation. We can do that. So we'll have minus Vs plus R times I, okay, plus Vc is equal to 0. And again, we could replace I with C dVc dt. Okay, and this would lead to the same equation as we've already seen. R times C dVc dt plus Vc is equal to Vs. So it's the same thing. Now you could get messed up if you decided instead of replacing I with C dV dt, you replaced VC with 1 over C, the integral of IC, right? At that point you're not getting, well, you have an equation that is valid, but it's in terms of an integral, and we typically don't write these equations in terms of integrals. We always write them in terms of derivatives. And so you want to make substitutions which result in time rate of change terms. Okay, and an easy way to remember this is that when you think of a capacitor, you know that a capacitor stores energy, and the energy of the capacitor is determined by the voltage across the capacitor plates, really the electric field, but it's represented by the voltage, and the energy stored is 1/2 CV squared. So what you want to do is, for whatever type of element you are working with, in this case a capacitor, if you recognize that the energy state of the capacitor is related to the voltage, then you want to make a mental note that what you want to end up with is derivative terms with respect to, or in terms of capacitor voltage, okay? That quantity that determines the energy state in your system. So for a capacitor, that's voltage. We'll see for an inductor, it's going to be current, okay? If we were doing some mechanical system, like a spring and a resistor, a viscous resistor, then for the spring, we would be looking at the force. Okay, the force across the spring dictates the energy that's stored, right? It's 1/2 k. It's 1/2 k x squared. So I said that wrong. Actually, I was correct in both statements. The energy stored is 1/2 kx squared, but the force is equal to kx, and so you can substitute F over K for X, and you end up with energy stored in a spring is 1/2 of 1 over K times F squared. Okay, so the energy stored in a spring is related to the force across the spring, and so you would, in a mechanical example, you would write a differential equation that would involve a time rate of change of force on the spring. Okay. So we're going to leave this here at this point. We're not going to go any further and try to solve this. Let's just consider a circuit with an inductor here and see if we can do the same thing. We'll come back and try to solve it later. So I'm going to draw a little bit different circuit here. I'm going to have a parallel combination of a current source and an inductor and a resistor. Okay, we'll say this is IS, and we'll call this the current IL, and we have a voltage VL across here. It's also the node voltage here. Okay, and what we want to do is we can write a let's see, if we write a KVL equation, and we would go around this loop right here. Okay. Do we want to do that? Let's, well, since I've written it, let's go ahead and write that. We'll write that IR. Okay, that's the current, really, IR. So when we go around that loop, we will have, this is the voltage, sorry, this. Maybe what I should do, I kind of boogered this up, but okay, we'll go with it. Okay, so this is VL. The reason for that is that I've got the positive IL current going down. All right. Recall that VL is equal to L dIL dt. Okay, or we could put the integral form as IL of t is equal to 1 over L integral of VL, okay, from minus infinity to time t. So KVL going around there, we'll have minus VL plus IR times R is equal to 0. Okay. And we can replace VL with minus VL with minus L DIL dt. Okay. Now IR is actually equal to IS minus IL. If you did KVL or KCL at the top node there, you would have that IR is equal to IS minus IL. So we'll go ahead and put that in there. We'll say IS minus IL quantity times R is equal to 0. Let's divide through by R, and we'll switch some things around. We'll have IS, well, let's do a sign switch. So you do L over R DIL dt. We'll have what was minus IL, but it'll be plus IL, and that'll be equal to IS. Okay? We can rewrite this as tau DIL dt plus IL is equal to IS, where tau is equal to L over R. Okay, and you notice that the form of this equation is identical to the form of the equation that we had for the capacitor RC circuit. So it's similar, or equivalent really, but it's, instead of voltage, capacitor voltage, it's inductor current. Okay. We could also do the same thing with KCL at the top node, but I'm not going to go any further at this point because we've established the two first-order equations that represent these two basic circuits, and so we'll leave it at that for now. So now let's look at the state equation. So let's recall the RC circuit, okay, where we had the differential equation tau times the derivative of the capacitor voltage. I'll write it as VC dot plus VC was equal to VS. Right? Now let's rearrange this so that we express V, the derivative of the capacitor voltage, with respect to everything else. We'll have minus 1 over tau VC plus 1 over tau VS. Now let's consider the case where Vs is 0. Okay, that just means there is no voltage source. So what we really have is a capacitor and a resistor in series. And we're looking at this voltage VC, and maybe there's some initial voltage on the capacitor, and so how does that voltage evolve over time? Well, it's going to discharge through the resistor. So if we have that, we can write VC dot is equal to minus 1 over tau VC. We can plot, make a curve here where we plot the dVC dt, okay, versus VC, and it will have a negative slope. It will be minus 1 over tau. Okay, so what does this tell us? If we had, let's say that tau was equal to 10. Okay, so if the capacitor voltage was equal to 10 volts initially, then the rate of change of the capacitor voltage would be minus 1/10 times 10, right? Or minus 1 volt per 1 volt per second. So let's write this out. Suppose tau is equal to 10 seconds. Then if VC is equal to 10 volts, then we have VC dot is equal to minus 1 volt per second. All right. If VC is equal to 5 volts, then VC dot is equal to minus 1/2 volt per second. If VC is equal to 1 volt, then VC dot is equal to minus 1/10 or 0.1 volts per second. Okay, so what it's telling us is that the rate at which the capacitor voltage is changing is related and proportional to the actual voltage on the capacitor. So when you have a large voltage on the capacitor, the voltage will reduce, will tend towards zero more quickly. But then as it actually approaches zero, at the rate at which it continues to approach zero slows down. Right? And what that's going to do is, let me see if we can plot this out here. Let me do it over here. I have time, I have capacitor voltage here. So maybe initially we have 10 volts. Okay? And so this has a slope of -1. Okay? -1. But then when it gets down to, say, let's do this, say 7.5 volts, right? At 7.5 volts, its slope is no longer -1, its slope is -0.75, okay? So it would have a slightly, this would have a slope here of -0.75 volts per second. So now it's going to go at a slighter slope. When it gets to, or shallower slope, when it gets to 5 volts, it will be even shallower, right? So this is -0.5 volts per second. And then when it gets down to something further here, to 2.5, right? Do you see what's going on? So what this actually ends up looking like is an exponential decay. Okay, we haven't proved that mathematically yet, but we're just kind of exploring how this might evolve. Okay, and it's going to be, it'll actually turn out to be something that looks like like 10, because it started out at 10, and then e to the minus time, and we'll find that it's time over tau. All right, we have yet to show that, to prove that, but that's what this is going to look like. So the conclusion here is that we can write a state equation which basically consists of writing how the rate of change of your state, the capacitor state, the voltage of the capacitor, how it depends on everything else in the circuit. Okay, and that's called a state equation. In future courses, or in a future course, you'll see how if you have some system that has several energy storage elements, if it's electrical, it could have several capacitors, inductors. Each one of those elements will have a state equation that will describe the rate at which its state changes in time as a function of all the other states in the system, as well as whatever inputs are forced in the system. And when you put all of those state equations together, you get a state variable. We call it a state variable representation of the system. Okay, so that's a little bit beyond what we're wanting to do here, but I wanted to just introduce you to that language. Okay, the interesting thing about what we just did here is that it kind of opens up the possibilities, or the idea of how you could actually solve this numerically with the computer, kind of in a discrete time manner. Okay, so I would rather be on a computer right now and have something like Excel open, but I'll try to show you this in the notebook here, and maybe you can try it out on the computer. So discrete time approximation. Okay. Discrete time approximation solution. So let's go back to this dVc dt. Okay, we can approximate this as some delta Vc with respect to some delta time. Which in turn can be written as some voltage Vc at some time 1, let's say, minus some voltage Vc at time 0, and then we would divide that by time 1 minus time 0. Okay, so what we want to do is let's define a discrete time variable. So let's do this. Let's say that t is going to be equal to some discrete index k times some delta capital T. All right. So this is going to be, this delta t will be our time step. So what we're going to do is we're going to set up a set of equations, or an equation that will allow us, or allow a program like a spreadsheet program to approximate the solution to this system by basically solving, given the state at sometime t0, can it predict what the voltage will be across the capacitor when we go delta t ahead in time. Calculate what the current state is of the capacitor voltages there, and then advance it another delta t, and so forth. Okay. So we can rewrite dVc dt as approximately the voltage Vc. Okay, but instead of Vc of t, it will be Vc of k times delta t minus Vc of k minus 1 times delta t. All right, so these are capacitor voltages at two discrete times that are separated by a time delta t. Right? And that will be divided by delta t, because that's the space between them. We can also write this as equal to Vc of k plus 1 times delta t minus Vc of k times delta t, whole thing over delta t. Okay, so now what we want to do, we also know that this is equal to, this is our state equation, right? So this is equal to, what did we find before? Minus 1 over tau Vc of, okay, now we have to decide what it's going to be equal to. Well, it will be equal to, in this case, if we use the second form, it'll be Vc of k times delta t, okay, minus, we saw, or plus 1 over tau Vs. All right, now let's rearrange this. Let's multiply through by delta t, and let's solve for Vc of k plus 1 times delta t. Okay, and I'm going to use a shorthand now. I'm going to say Vc bracket k plus 1. Okay, what that means, this right here is equal to this. Right, it's just a shorthand. Vc of k plus 1 at time k plus 1, which is k plus 1 times delta t, is going to be equal to Vc at time k, right, minus delta t over tau times Vc at time k plus delta t over tau times Vs. I should say Vs is at time k as well, because Vs could in general be changing with time. Okay? So let's say that you had a spreadsheet, okay, Excel spreadsheet, and we had a column called time, and we had some, maybe this is some index k, okay, and we'd have 0, 1, 2, 3, 4, so on. And then we have somewhere over here defined delta t equal, and we'll choose some, let's say that was 0.1 seconds for now. So t here is going to be equal to k times delta t. So it'll be 0, 0.1, 0.2, 0.3, 0.4, etc. Okay. Then we'll have Vc of k. Right? And right here will be our initial condition. Initial condition. Let's assume, and for this case, let's assume, or let's ignore Vs for right now, just to simplify. But you can easily add Vs in. So we'll ignore Vs, and we'll say the capacitor, the first entry here in row 0, is you would place a value in for Vc. That would be the initial condition. Let's say it starts at 10 volts. Okay? And then in here, you would have, if this is row, let's say this is row 2, and this is column, this is A, this is B, this is C. Okay? The formula you'd put in here would be, this is equal to C2, okay, that's this guy here, right, minus, and then what we'd want to do is we want to define a tau over here. Somewhere else in our spreadsheet we'll define a tau. Let's say it's, what did we say, it was 10 seconds. Okay, so C2 minus, and then what we would have is delta T over tau, right? So you could define name ranges for that, use variables there, times, and then we're going to do times C2. If you wanted to add in Vs, you could do Vs over in column D, and you could say plus, delta T over tau Vs, which would be equal to, let's call it D2. So this would be Vs at time K. Right. And then here you would do C3 minus delta T over tau times C3 plus delta T over tau D3. Right. And you just copy all this down. And what you'd find is that if you plotted Vc, okay, column C versus column B, or time, you would find that this would start at 10 volts and it would decay. Now, depending on how you choose delta T, you would either have a very choppy, you could see the line segments here, or if you made delta T real small, you would get a more accurate solution, and eventually you would get one that would be, sufficiently accurate for, whatever the problem is that you're trying to solve. Okay, so I'd recommend that you try this out in Excel. It's actually pretty neat, and it's especially powerful if you want to program in some arbitrary Vs, right? That becomes much more difficult to solve the response for an arbitrary Vs. We won't actually do that in this class. We'll be very specific about the types of forcing functions, if you will, the voltage sources or current sources that will drive the system with. They'll be constant valued. They might step from one value to the other, but beyond that, that's about all we'll do. And then later in the course, we'll look at if Vs is actually just pure a sinusoid, okay, purely sinusoidal. But those are the only type of signals that we're really going to look at. But if you set up a little simulator, and you can do this in Excel, you could simulate and solve a state equation, this differential equation, for any arbitrary input. Okay, now we want to look at comparing the state equation versus the circuit, node, or mesh equations. And we're going to get there where we're going to solve these the state equation, but we're not quite there yet. Okay, so at this point, prior to introducing capacitors and inductors, we were dealing with resistive circuits that would have, voltage sources and current sources, and we found that if you solve such a circuit where you'd have several sources and you're looking, say, for some output, call it this current right here, I, this was R4, IR4, we could say this is some weighted sum, right? Say K1 times VS1 plus some K2 VS2 plus some K3 IS, right? Where K1, K2, K3 are just functions of these resistors. At the end of the day, they're just a function of these resistors. Right? So what I want to try to do in this section here is to try to connect what we've done so far with the state equation to what we knew in the past, and try to show you that actually we haven't switched things up on you. This is all consistent with what we have done in the past, and you can still write the output of the system as a superposition or weighted sum of all of these basic sources. But we have to do a little caveat. We're going to modify our statement and say that the output or the response of the system is going to be a weighted sum of all independent sources and all energy storage elements. Okay, and I will try to derive that now, or show you that. So note that, okay, for capacitor and inductor, dVc dt and dIL dt, okay, are finite, right? Meaning that Vc and or IL cannot change instantly in time. Okay, if you zoom in enough in time, if you limit yourself to a short enough window in time, you can treat the capacitor as actually having a constant voltage. Okay, that's the key. If you zoom into a small enough window of time, you can represent the inductor as a constant current source. Okay? So what this allows us to do is we can treat capacitors as like a voltage source, and we can treat inductors as a current source, and we can solve our circuit just like we did before we ever knew capacitors and inductors were around, and write our response as a superposition or weighted sum of our independent sources and our capacitor voltages and inductor currents. And then what we need to do is write a state equation for each of our energy states in our capacitor or inductor to describe how the voltage on the capacitor evolves in time. So it's kind of like you have a time-varying voltage source. But the difference is from a truly just time-varying voltage source that you might dial up like on your function generator. In this case, the time-varying nature of our capacitor voltage source is that the variation in time of its voltage actually depends on what's going on in the circuit. Okay, so it's not independent of the circuit. It's all kind of coupled together, which is what makes solving these circuits both challenging and interesting at the same time. So let's look at an example here. Actually, let me write this out. So therefore, okay, we can treat capacitors as a time-varying voltage source, okay, and inductors as a time-varying current source. Okay, so let me show you an example. So here we have a voltage Vs, we have a capacitor C, we have a resistor R1, and another resistor R2. Okay, and this is voltage V2, and we'll say this voltage at this node here is V1. So we have these two nodes here that are of interest. I should put C's over here. Okay, and we'll define current going around clockwise. So we're going to define, let's see, well, let's do what I suggested, that we would replace this voltage source, or this capacitor with the voltage source. So we'll redraw this, and what I'm going to do is actually draw it as a triangle, okay? And I think I did it backwards. It's a plus and a minus here, okay? I wanted to do it that way. I did that because of the current direction, okay? IC is going this way. And and we have our two resistors, R1 and R2. And we will call this VC, and VC is equal to 1 over C, the integral of the current IC. Okay? So let's write a KVL equation. Okay, so here we're going to, let me just say, replace C with dependent V source. Okay, so let's do KVL for our circuit. We'll have, this is I, or IC. We will have minus Vs plus Vc plus R1 plus R2 times IC is equal to 0. Okay, and we can solve for IC. IC is going to be equal to Vs minus Vc over R1 plus R2. Right? And then we could solve for if the response we're looking for is actually VO. Right? So find, not VO, V2. Find V2. We can write, well, V2 is just R2 times IC, which is equal to R2 over R1 plus R2 times Vs minus Vc. So we therefore write V2 as a function of time is R2 over R1 plus R2 times Vs minus Vc, and I'm going to put this as Vc of time. Okay, so at any given moment in time, if you knew the capacitor voltage, you could write V2 as just a weighted sum of the independent voltage source and the current voltage of the capacitor. Now this is not sufficient to solve the problem because we don't know how Vc changes in time. Right? So we have to write a state equation to actually describe how the voltage changes. So we say now we need a state equation for Vc, or the capacitor. So we would write dVc dt, right, is going to be equal to, and remember it's C dV dt is equal to IC, so we'll write 1 over C times IC. Okay, but what we really need to do is we want to express IC, we want to express dVc dt in terms of the capacitor voltage and in terms of the independent voltage source Vs. So let's replace IC here with what we found here. So we can write that as Vs minus Vc over R1 plus R2. Okay, and so between these two here, this is a complete solution. Right? Now you may wonder, wait a minute, this is like more than what we had before. We had just one equation, one state equation. And that's true. We have this equation here. I can rearrange this and write this as, let's say, C, or let's say R1 plus R2 times C dVc dt, right? And then plus Vc is equal to Vs, right? And this is a tau here. Now it's different. It's got an R1 plus R2 because this circuit has two resistors in series rather than just the single one that we looked at before. But this is right here. This is same as found previously. Okay. So if all you're looking for is how does the capacitor voltage evolve in time, then you just need the state equation. But if you're trying ultimately to solve for some other node voltages or mesh currents in your circuit, then you're going to need to go through doing nodal or mesh analysis. And in that case, the way you can go about doing that nodal or mesh analysis is by treating the capacitor voltage or the capacitor as a dependent voltage source and write whatever node voltage or mesh current you're looking for in terms of a weighted sum of sources, which would include the capacitor voltage as a time-varying source. Let's look at one more example. Okay, This is a little bit more involved. For volts 1 ohm, another resistor, a 1 microfarad, 2 ohms, a 3 ohm, and then a 1 amp. Okay, and we have nodes 1, 2, 3, and 4. Okay, and we'll say that this capacitor has initial voltage of V2. Oh, V2 is going to be, I'm sorry, not initial, take that back. V2 is equal to VC, and it has an initial voltage of 2 volts. Okay, so the task is solve using nodal analysis. All right, and we want to find voltages for V3 and V4. Find V3 and V4. Okay, so let's do KCL. Let's see the node voltages that we don't know. We know node 1, and we're gonna treat node 2 like we know it because it's a capacitor voltage. So the two nodes we don't know are node 4 and node 3. So let's do KCL at 4. Okay, we will have V4 minus 4 volts over 1 ohm plus V4 minus VC over the 2 ohms minus 1 amp is equal to 0 volts. Okay, and we can note that at time equal to 0, we said that the capacitor voltage was equal to 2 volts. So therefore, we can write that V4, let's say, times 1 over 1 plus 1 over 1/2 is equal to 1 amp plus 2 volts over 2 ohms. Okay, so that means V4 at time 0 is going to be equal to 4/3 of a volt. Okay, that's just at time 0. Now let's do KCL at node 3. Okay, and we'll have minus 1 amp leaving plus V3 minus V4 over 3 ohms is equal to 0. So that will lead to V3 is equal to 3 volts plus V4, and we can also write what the voltage will be initially at time 0 at V3. It will be equal to 13/3 of a volt. Okay, so we can write that V4 of t is going to be equal to 2/3 of an ohm times 1 amp plus 1/2 or 1 over 2 ohms times VC of t. Okay, and we can also write, or we can rewrite it as V4 of t is equal to 2/3 of a volt plus 1/3 plus 1/3 times VC of t. And we can also write that V3 is going to be equal to 11/3 of a volt plus 1/3 of VC of t. Okay, at this point we haven't dealt with how the capacitor voltage changes with time, so we need a state equation. Okay, so we can do that by writing a KCL at node 2. Okay, so we'll do KCL at node 2. And what we have is that IC plus VC minus V4, VC minus V4 over 2 ohms is equal to 0. IC is equal to C dVC dt. Right? Plus 1/2 of VC minus 1/2 of V4. So we can Now, V4, we already have expressed V4 in terms of, and we have it right here. Let's pull it over here. I'll take this, we'll plug it in here. Okay, so that will give us C VC dot plus 1/2 VC minus 1/3 of volt minus 1/6 of VC. That's equal to 0. And lastly, we can rewrite this now as dVC dt is equal to, let's see, we're going to collect our VC terms. So we have 3/6 minus 1, 2/6, or 1/3. Is that right? Let me double check. Okay, I think this is minus 1/3 VC plus 1/3 volts. Okay, I think that's, check my arithmetic, but I think that's right. Okay, so what we have now is we have solved for the two unknown node voltages, V3 and V4, and we expressed them in terms of our, our 1 amp source and our 4 volt source. That's what created these two terms here. And then we have an additional term that involves VC, and we have a state equation that expresses how VC changes with respect to time. And so between those two, if we solve the state equation, we know how VC evolves in time. Then we can plug that in to our two expressions for the node voltages V3 and V4, and we can describe how those voltages change in time. Now, note a very important consequence here, that if you have a circuit that involves a capacitor, but it has a lot more circuitry than just one resistor. Like you see here, there's 3 resistors, there's 2 independent sources, and then there's the capacitor. Even so, every single branch current and every single node voltage, or branch element voltage, all of these currents and voltages change at the same rate that the capacitor voltage changes at. Okay, so that's comforting to know that if you can solve the state equation and you find that, okay, this thing has an exponential decay and it's got a time constant of so many, 10 seconds, then everything, all the currents and voltages in that circuit are going to change at that same rate. They'll have the same form. Okay, and that can help us actually get pretty far, or have some pretty good insight into how the response of the circuit at different points in the circuit, if you will, are related or really dependent on the state equation for this capacitor. And the same thing would hold if we were solving an inductor circuit as well.